So today we are going to start inclined portal frames. Now I hope that you have very well understood the previous lectures related to the plastic analysis, especially the ones related to 2D frames. Now the inclined portal frames, they have some difference. And what is the difference? Let's say we have a inclined portal frame, and at the beginning we are considering a symmetrical inclined portal frame, and let's say it's under a horizontal and vertical load, point loads. Now my question is that what are the possible mechanisms, and for that purpose what we need is we need to draw the bending moment diagram. Now the nature of the bending moment diagram could be different if it's under horizontal load and under vertical load, so they may be slightly different, the number of nodes where hinges are possible. So let's say we are first drawing for the case of the portal frame under vertical load. So under vertical loads, this would be the bending moment diagram. If it's under horizontal load,
the bending moment diagram will be different.
that is at the crown, the peak will not be there, it will be just zero bending moment at the crown. Okay, so under horizontal load, both the columns, they will have identical bending moment diagrams, unlike the case of the vertical load, and the bending moment in the case of the top beams, it will be zero at the crown. Okay, what will happen if for example the structure is under combined horizontal and vertical loads? So what you can do, you have to superimpose these two diagrams in that particular situation. So what we find is that under vertical loads it has 5 possible hinge locations, under horizontal loads it has 4 possible hinge locations. So how many hinge locations you expect under the combined action? So we would expect 5 hinges under the combined action. Alright. So when we have the combined horizontal and vertical loads, in that particular situation we can compute what will be the n minus r, and that will come out to be 2. So that means this predicts that there are 2 possible mechanisms, right? But now this has similarity with the regular frames. So what are the possible mechanisms? So you can make a guess. So first idea which will come to your mind will be something like beam mechanism, because beam mechanism looks to be an obvious choice, but will that be possible here? Beam mechanism, try it in you with your paper and pen if beam mechanism is possible. And then we may have the sway mechanism, because here definitely we have the horizontal load also. and then there could be combined mechanism also. But here now the combined system will be different from what we have learned, or there may be any other mechanism also possible, because we are venturing into a new area, new type of structure. Okay, so these are possible issues which we should keep in mind. So let's consider now. Let's consider a symmetrical frame under just vertical loading, and later on we will also explore what happens if it's under the combined action of the horizontal and the vertical loads. So we are drawing this portal frame and we are just applying a vertical load. Now think, is beam mechanism possible here? So beam mechanism, we need 3 hinges in the top beams, top of the columns, then the crown, both left and right columns. So now is it a mechanism? It is not a mechanism, it's a stable structure. What prevents it from being mechanism? The reason is that the axial effect of the members will come into action. So it's just like a truss section now. So this will not be a mechanism. And then you can also convince yourself that, let's say if it's under combination of horizontal and vertical loads. Here we have applied only vertical load, but suppose you are even applying horizontal load, then also this beam mechanism will not be possible. So that means beam mechanism has to be ruled out. Alright, so we rule out the beam mechanism and we explore other possible mechanisms. Now, is sway mechanism possible? Try to draw on your paper and pen the sway mechanism, because beam mechanism we have got a surprise. Possibly we did not expect this to happen. For sway mechanism you can just apply the horizontal load first, and then we can apply both the horizontal and the vertical loads together. So I hope you have now drawn the sway mechanism in your own notebooks, and now let's compare here. So your conclusion, I don't know what conclusion you have got, but here our conclusion, let's see based on this drawing whether sway mechanism is possible or not. So in sway mechanism we need 4 hinges, top and bottom of the columns. So if it's under even combination of the loads, so sway mechanism is also possible. But then under pure vertical loads, you may eliminate sway mechanism as we have done in the case of the regular frame. So sway mechanism is in general possible under a combination of horizontal and vertical loads. And now we will consider the other mechanisms which are possible, that is the combined mechanisms. Now we begin with the beam mechanism. Can we do something with the beam mechanism to convert into a real mechanism? Because the beam mechanism system is not a true mechanism. So if we just do little tweaking of the beam mechanism, we can get something called as a beam column mechanism. So how do we obtain this? We tweak the diagram of the beam mechanism, and if we can increase one hinge somewhere so that the structure becomes a mechanism. So in the earlier diagram of the beam mechanism, which was not in fact a mechanism but the beam mechanism system or beam mechanism configuration, all we now do is we create a hinge at the bottom of one of the columns. So first what we have done, we are just marking here the hinges for the beam mechanism. And this is not a mechanism, but if we create one more hinge, will that be a mechanism? And where we can create the hinge? Either on the left column bottom or the right column bottom, does not matter. So if we create one hinge extra over and above this configuration of 3 hinges like this, so is it now a mechanism? Is it a stable structure? The answer is no, it is no longer a stable structure, and it will drift like this to the right. The remaining structure will just collapse like this. But now here we are showing that it is drifting to the right. Can it drift to the left? That is one question. Think about it. Can it drift to the left? If yes, how? If no, why? Yeah, here is the answer, that it can only drift to the right side because gravity is acting. So gravity is preventing drifting to the left. Similarly, we can draw its mirror image also. Here we had created hinge in the bottom joint of the right column. So let's create hinge in the left column bottom. So we'll get similar results. So we have the same 3 hinges for the beams, and then we have created one extra hinge in the left. So now it will drift to the left. It cannot drift to the right because gravity is there on the top. Gravity is acting on the top beams, so that will definitely prevent drifting to the other way. Now this is called as the beam column mechanism, because here there is a combination of the beam mechanism and then there is one hinge at the bottom of the column. So one column fails and the 2 beams, they undergo hinge formation. Now can we get a combined mechanism? Let's do superposition. So you also try in your own notebooks. So what we superimpose the sway mechanism and the beam column mechanism. So sway mechanism you have understood and the beam column mechanism you have understood. Just try to superimpose them. So remember, in the case of the sway mechanism, the crown does not have hinge, and now we have the beam column mechanism, and you have to superimpose and also check where there is any hinge cancellation. So now you try to superimpose them, and will there be any hinge cancellation? So here there will be a hinge cancellation at this joint. The top of the left column, there will be hinge cancellation, and the first column, left column, and the just beam, inclined beam connected to it, they will act like a rigid body now. So now this triangle ABC, it remains like a rigid body and it undergoes rotation about joint A. So now D also undergoes displacement. D goes to D dash, and the displacement such that the movement of D is at right angles to its original length, and then we join C dash and D dash. So this is the combined mechanism. So this line, how does the movement of C happens? So basically C moves normal to the line AC. So we assume that the rotations, they are very small, these are virtual rotations. All the three members, one member I am counting ABC as single member, then we have CD and DE, they undergo rotations and they are all related to each other. So all we have to do is, in order to set up the equations of the external and internal virtue work, we must find out the relationship between these three rotations. So that's what we'll be doing for both the mechanisms. So first we'll begin with the beam column mechanism. So let's first write down our assumptions. The very first assumption is that all the members, they are inextensible. Okay, and now we have the second assumption. So structure we are considering at the verge of collapse, and then we are giving infinitesimally small displacements and our rotations. So when we are applying the virtual displacements and rotations, then let's see what are our main assumptions. So how we are doing it. So we either apply rotation to a member about its own end, or we apply rotation to the member about some other center. So basically members, they undergo rotation, and these rotations we check at the two joints of the member, and we then multiply this rotation with the plastic moment capacity. So member could undergo infinitesimally small rotation about its own end. It may undergo rotation about some other center. Okay, so these two cases we are considering. Now our assumption is that when this kind of rotation occurs, so this rotation is very small. So relatively the member lengths are very large. So that means essentially the other end of the member, although it sweeps a circle, theoretically speaking it sweeps a circle, but because the rotation is infinitesimally small, so the arc length can be considered as straight line. So arc length and tangent lines, they are one and the same, and for us the effect is that the end point of the member is moving normal to its original length, like it's shown here. So please note that all the arc lengths we are considering that they are like tangent lengths. That is our assumption. So in this process, the condition of inextensibility holds good. This we had the assumption in the case of the stiffness approach also. So we learned that the members, if they are considered inextensible, then if they are undergoing any displacement normal to their own lengths, their lengths are not changing. Now with this information, let's do the analysis of the beam column mechanism. Now what do we mean by analysis? Basically beam column mechanism, what we have to do is we just try to write the equation of the virtual work, both the external and the internal, because that gives us the failure load. So right now for this problem we are considering the structure under vertical loads for simplicity, and once you understand this, then you consider it for the combined action of both the vertical and horizontal loads. That will be your homework. So now please pay very careful attention to how we are doing it. So vertical load is acting at the crown, see, and this is the failure load of this particular mechanism. So we can consider either the case that the bottom of the right column is hinge or the left column is hinge. So here we are considering the right column, that is point number E, hinge. So that means the drifting will be towards the right. So if right column is hinged, the components they drift to the right. So now what we are doing, we are extending BC and we are also extending ED, and both of them they meet at an external point, and we are calling this point as I. And why we are using I symbol? Because this is an instantaneous center of rotation for applying virtual displacements. So basically what we will be doing, that the structure is at the verge of collapse, and now at this stage we apply a very infinitesimally small rotation about this instantaneous center of rotation I, and this rotation is equal to phi. Now see how the various points they move. So now you can imagine yourself, this will give you option to think. So now D, how it moves, you pay attention to triangle ICD. So triangle ICD, it undergoes rotation about I. So this triangle ICD, it remains rigid. So accordingly, we can say that C moves to C dash and it moves normal to BCI. And similarly, D moves from D to D dash and it moves normal to EDI. And both the displacements, they are very small, so arc lengths can be approximated as tangent lines. And then we join. Now we see what are the rotations undergone by various members. So now the member CD, how much rotation it undergoes? So this member undergoes rotation exactly same as the applied rotation phi, because the triangle undergoes rotation like a rigid body about I. So this is phi, and let's say the rotation of member ED is alpha and the rotation of member BC is theta. So once we have this rotation, we can very easily say that the work done at E is mp into alpha and work done at B is mp into theta. Now what will be the work done at C? Because now C, there will be now the net rotation equal to theta plus phi. So here at C, the work done will be mp theta plus phi. And similarly at D, the work done will be mp alpha plus phi. So I hope this is clear, like in the case of the regular frames. Okay, so these different internal virtual works, they are as per the rotation. So this BC undergoes rotation theta, DE undergoes alpha, and CD undergoes phi. So net rotation at joint C, because joint C, it undergoes a net rotation because the angle increases by this amount, theta plus phi, and joint D, its angle closes, its angle was larger, now it is smaller, and the amount is alpha plus phi. So let's continue further. So note that this we have already stated, CC dash is normal to BC and DD dash is normal to ED. So theta and alpha, they are to be related to phi. So let's do that. So all we need is just the information of trigonometry for this purpose. So DD dash is equal to ED into alpha, that is the arc length. And this is also equal to ID into phi. Alright. So this gives us a relationship between alpha and phi. And similarly, we have to get relationship between theta and phi. So what is CC dash? CC dash is basically BC into theta, and this is also equal to IC into phi. So this gives us relationship between theta and phi. But now we need to just use the trigonometry and find out the lengths of this triangle involved. So for that purpose, we just draw the structure again and try to find the various lengths. So let's assume some dimensions for simplicity. Let's say the columns are 5 meters in height. And let's also assume that the height of the crown portion is 2 meters, and then the horizontal projection of the two beams is also 5 meters. Now we just extend the two and we go into the instantaneous center of rotation. Now we'll make use of similar triangles. So BC, you can get the value as 5.38 meters. And we also mark a point F here. So we just make use of the similar triangles. What are the similar triangles? BCF and BID, they are similar triangles. So making use of the similarity, CI is also 5.38 meters. So now what is ID and ED? ID is 4 meters and ED is 5 meters. So we get the relationship. Alpha is 0.8 times phi, and for theta and phi they are exactly equal because IC and BC, they are both equal to 5.38 meters. So we get this relationship that alpha is 80% of phi and theta is 100% of phi, and we make use of this relationship now. So let's zoom now this portion, because we need to find out what is the vertical displacement of C. We are now zooming this portion because that will tell us the external virtual work done by P. So let's draw this. So I'm just drawing it in a corner. So now we are drawing this C dash. So C dash, its length is basically BC into theta, and we are drawing here two lines, extensions, so that the two meet each. C double dash is the vertical displacement of PU. So now this angle, what will be angle C double dash C dash? So this angle will be gamma. Just convince yourself that this angle will be gamma. And once we have this information, then the vertical displacement can be expressed in terms of theta. So this vertical displacement C double dash will be simply equal to C dash cos gamma. And what is C dash? It's BC theta into cos gamma. And now what is BC cos gamma? Just see the diagram. What is BC cos gamma? So BC cos gamma is the horizontal projection of BC, and that's equal to 5 meters. So the vertical displacement is 5 theta. So now we have derived these relationships, and everything, all the rotations or displacements, they are expressed in terms of theta only. Theta is the only variable, so that we can cancel it out on both the sides. So we are now writing the equations of the internal and the external virtual works.
So the external virtual work is equal to Pu multiplied by the vertical translation of Pu, that is CC double dash, and the internal virtual work we can write at various points, like at B the work done is MP theta, at C it is MP theta plus phi, at D it is MP alpha plus phi, and finally at E it is MP alpha.
And now we need to check the yield and the equilibrium criteria. You can check it now or wait for the next mechanism. So here we have checked one of the two mechanisms. So this answer Pu equal to 1.12 MP is basically valid for the beam column mechanism. We should also check for the combined mechanism, and then we should do the yield and equilibrium check for the lower of the two. But now we have solved till this stage, so if you want to do further in-depth analysis, you can do the equilibrium and yield check for this mechanism also.